Okay, good morning, students. Today is November 8th. And today we're going to do three things. First, I would like to select some of you and ask you to explain how did you do the assignment, okay? Then I would like to comment on how to implement this process in a computer program, okay? And finally, at the end, I would like to explain the new assignment. In the new assignment, probably you read in the SID web, is to be completed as teams, okay? By teams, by group of students. But you have to be careful because the group of students has to satisfy certain restrictions. We're going to insist on that. And I'm going to ask Engineer Isaac to say a couple of words about the system that you have to analyze. And you will see that it is well related to what we did last semester, okay? So that's the agenda for today, okay? Is there anybody who wants to explain how he completed or she completed the assignment 3, the first part? Anybody? Once you raise your hand, or you want me to select somebody? You tell me, please. Is there any volunteer? Any volunteer people?
Yes, I can explain.
Okay, so you are Mr.
Jimenez.
Jimenez. I'm going to give you permission to share the screen. Let me get here. You are.
Okay, let me open the.
Now, I make you co-host so you can share the screen.
Okay.
Go on.
Give me a second, Doctor.
Sure, no problem, no problem. The other students, please, I would like to ask questions if you need. See, something is not clear. So today, Mr. Jimenez will take my place.
Just need to explain the first problem.
No. The second one is
the second. Okay.
Yeah, please.
Okay, Doctor. Second problem. Yeah, it's here. Can you see my screen?
Now yet. Yeah, I can do.
Yes.
People, just a second. People, can you see Mr. Jimenez's screen? Anybody who can confirm?
Yes, doctor.
Yes, doctor.
Okay, go on.
Yeah.
Go on, Jimenez.
Okay, for the second problem, we have to analyze the longitudinal transversal stiffener. Yes, yeah.
Mm-hmm.
For this, we're going to consider the second response, the shield, right?
Yep.
We can take the load over the bottom and consider two tanks, one empty, just one full. We have the load over the structure from these parts. We can model I model like that. For example, when we check the last class, you say that in the first joint we had the clamped and this end clamped and the top is clamped. But in this point, just we have rotation. No? We don't have an displacement, vertical displacement. then we're going to see it's a X drop. Here I going analyze for the 5 element. I can guess the rotation in this, the second one in this rotation. For this, this is the distributed load over the lateral load over the beam, right?
Yeah.
You have the consider this equivalent load of and on the ends the beams, right?
Yeah.
Yeah. Now for the longitude in this part we have the effective nodal force. It's like the action of the force, like the reaction on the force and the equivalent force on the ends, right? For example, this is value and this is the bending moment.
No, that's not bending moment. That's external force. External moment. External moment.
Right.
Please remember, there is a difference between external and internal forces. Okay, go on. Sorry.
Yeah. Exactly. I'm sorry.
No problem. No.
For the longitudinal, we got the consider the geometry condition, right? For each node, and we have this lateral load. For that, is the same value for the downward and upward in this part, just from the second node to the fourth node. Just we have that, yeah. And here we're going to use the same part to the right. We got the same length for the each joint, right? For each element, we have this part. In this part, in the second node, we got the same external moment, and this cancel, right? This is the equivalent system. We got the global Stephen matrix and the force vector.
Just a second there. Anybody has any question, any comment on this matrix? Mr. Arias, do you have any comment, please, on this?
And I don't use these metrics. I use another metrics.
And why is that different matrix that you use?
I use the metrics that is symmetrical to the diagonal.
This is also symmetrical.
Yes.
But in the metrics that I use, I put the cosine and sine and the inertia.
He's using also the inertia here.
Yeah, but I don't.
The same inertia along the.
Yeah, I know. There is something that I don't like here, but I want you to see somebody to point on that. Mr. Zambrano, any comment on this matrix, on this system of equations? Mr. Zambrano?
Good morning, Doctor. No, I cannot see the error, sorry.
No, I'm not talking about error. I'm just talking about differences. Ms. Pinkai, can you say something about this matrix? Any comment?
I also use the matrix that has sine and cosine for the element 5 because it's vertical and has an angle with the global reference system.
So, but as a result, for example, in this case, how many degrees of freedom did you include in your work?
18.
18. So you have 8 more than him. What's the difference?
Yes.
What's the difference?
I didn't simplify the distributed force.
No. There's something extra. There's some, let's go on. Miss Gutenberg. Any comment on this matrix?
No, I think no.
No?
Doctor, I think that
Who is talking? Who's talking? Who's talking?
Arias,
Okay, go on.
Jimenez don't consider the force in direction X.
Yes.
Uh-huh.
That's the problem. That's the problem. Why? Because remember, you right now, you are working in the global reference system. So for example, on the vertical element, you have this force, right? And that force is horizontal. And on the bottom, you have this force, which is vertical. And because of that action, both tend to rotate. So you have to have forces in the X, forces in the Y, and rotations. So you have to have, for every joint, you have to have the three degrees of freedom. Okay, go on. Let's see what you obtain, Mr. Jimenez.
Okay. Yeah, just analyze the beam bending here.
Yeah, but the problem is that, see, the bending,
Yeah, I know.
the bending in the vertical is different than the bending in the horizontal. And both have to be linked. Yeah, go on.
I got it.
Okay.
Yeah, so later, just I need to obtain the rotation here.
Okay. Yeah, you obtain the rotations. Only rotations,
Yes.
right? Yes.
Yes, just
okay.
only the rotation for this matrix.
Okay.
But then when we have just
but see, which is very
the moment
very strange. Not very strange, but is that you are not including values so far. It would be easier, instead of handling all of these equations, replace the matrix by values and solve it.
Okay, replace the reason here.
Yeah, but what I'm saying is that instead of having it with just symbols, it would be easier to work with values. Okay, let's see if we have somebody else. With,
okay.
Okay, thank you, Mr. Jimenez. Thank you. Anybody else? Any other person who wants to share his or her work? Please. Anybody who wants to share his work, or you want me to select somebody? Please, I need volunteer. Come on, people, it's Monday. No? Okay, what I'm going to do, I'm going to select. Okay, Mr. Cano. See, I put it a random number on each name. So I have the largest number is 0.899. Mr. Cano, is here Mr. Cano? Mr. Cano, are you here? Are you there? Mr. Cano? No? No, it's not here. Okay. Mr. Galarza? Mr. Galarza?
Good morning, Doctor. I'm here.
Okay,
but
so
I just have a problem with my Zoom. When I share the screen, the computer crashes. So
let's do this. Okay. Let's at least try to explain. Okay, what I can do is this, try to explain your work, okay? Especially emphasizing in the differences, if there are some differences with the previous work, which was presented by Mr. Jimenez.
Okay.
Okay, in the meantime, let me try, or let me do something. Let me try to open the seed web, and I can see your work and I can present it so you can be able to explain it. Okay. So here we are. That is 3A. And speed reader. Okay, let's go to Galarza. There you go. Oh, it was easy. Okay, let me share the screen. Okay, can you see your work, Mr. Galarza?
Yes, yes, I can see. Look.
Okay, so let me try to enlarge if I can. Okay, go on. Let's go to problem 2. This is your work. This is not. This is so here. Okay. You tell me if I should go down or up. Okay.
Yeah. Okay. Yeah. So first, I was a little confused with the matrix that I have to use. So I have to check the previous class. And in one class, you show us how to overlay the effect of a beam and a bar.
Mm-hmm.
And I tried to solve that system, and then I put it together, and I found a matrix 6 by 6.
Yeah.
Yeah. So with that matrix, I started to work it.
Okay.
First,
let me go down. Let me go. Okay, go on. Go on.
This is the discretization. I consider 5 elements and 6 joints.
Okay.
6. Yeah. Please go down. And then I found the reaction forces applying the method that is attached in the homework.
Okay.
I split it in the notes and I get that values. And then
all of these values.
Yeah.
Okay. So you have forces to the left, forces upward, and you have moments. Okay. Good.
Yeah. Mm-hmm.
Good.
That is in the vertical. The forces in the left are in the vertical reinforcement.
Okay.
And then I found the stiffness matrix for each element in Excel.
So this is this.
That is, yeah.
2,
for the second,
3, 4, 5. Okay.
Yeah. And then I have to put all in the big matrix. So I have to find
18 by 18. Right.
And I put the elements. I mean, from the horizontal stiffness, I put like 1, 2, 3, 4 aligned.
Yeah.
So it was easy to put in the big matrix.
Let me go back just a second. Okay. 1, 2, 3, 4. Oh, this direction. And then 3, 6 is what it was more
confused. Yeah. That was a different one.
That was the element 5.
Yeah.
Yeah, this element 3 and 6. Okay. Go on.
Yeah. So then if you go down, so here to solve this matrix, I did the process that you teach us in class.
Mm-hmm.
That put the forces and the condition, the geometric condition. And if you go down, I have the solution. And I found that displacement.
Yeah, the displacement you see here in the first joint is not 0, but it's very small, very small. Yeah, okay. Similar
here.
Mhm.
And then I have the results, and
I'm sorry. Oh, this is feet. This is feet.
yeah, feet, and the force is in tons, and the moment in tons per feet.
Okay.
And then I try to compare with that values, but honestly, I get a error bit higher.
Okay.
But I think that it doesn't is about Excel, because I proved with the exercise that we did in class and I obtained the results. So
So
the
you
only
check.
thing that I
You check.
think that I have to check is the forces, because with that forces we solve the matrix and
Yeah.
all depends on the forces.
So
I
this.
was a little bit confused when I tried to determine the force.
Okay, but I think the problem here is that in the joints, that's something that we were discussing last night. Okay, let me try if I can draw on this screen. Is it, yeah, can I? No, I cannot. I cannot draw in here. No, you cannot draw here. I cannot draw. I cannot draw here. But the thing is this, okay? Let me go back. Let me go back. For example, this is the moment, right? Now, this moment, okay? This moment is not the total moment here. It's not the reaction moment here. This moment is just because of the load here.
Okay.
Okay, so when you obtain the final value, this value here, okay, this minus 25.7 is equal to the reaction plus the value up here, plus this one here.
Okay.
Okay, so what you need to get this value on the right hand side, and then you will obtain the reaction. Okay.
Yeah.
So that's something that we have to do. Yeah, this process here is something that we learned when I was here at the university. And it was called the moment distribution method, or the Hardy-Cross method. So what you did was you start with a certain values, and then you went on. And see, the thing is that in this point, when you have a connection, the moment has to be distributed. And that distribution depends on this K factor. And this K factor depends on the EI. Okay, and a stronger beam would take more moment than the others. And eventually, what you have to do is in every joint has to have an equality, something like this. So you try to iterate in order to reduce more and more the difference. Okay, so yeah, that was a very nice exercise in the past. Okay, good work, Mr. Galarza. How many hours did you spend in this?
So I spent like 20, 25, but I put like 16 because
Okay.
I have to correct something.
No. That's a good work, except for the last comment. Thank you. Thank you very much.
Okay. Thank you.
Good work. Let's stop sharing this. There's just so many things open. Okay, do we have time for one last comment on somebody? I would like to see. Mr. Barba, did you complete the assignment?
Good morning, doctor. Yes, I am complete the assignments.
Can you share the screen with your assignment? Can you?
Yes, of course. One moment.
Let me give you permission. There. And you can share now your screen. Okay, let explain us the first problem, please, Mr. Barba. The first problem. I can listen to you. Are you talking, Mr. Barba? Oh, yeah, your microphone is off.
Okay.
Go on.
Well, in the first problems, I analyze one beam with the half one force in the Earth's over two, one moment in L, in the position L, with an analytical method, we define the function of the integrate. We obtain this equation of the moment. Well, I define the boundary condition, and replacing, I obtain this value of the constants, and the constant A and constant B.
Okay, but M1, you do not know M1, right?
Okay.
Go on.
Well, and I'm going to define the equation of the moment that this forms with relation with the deflection. And I'm going to integrate after obtain this function of the deflection, and I have two constants. But in this case, I'm going to analyze this equation in two elements. What the first elements we're going to analyze is the L over 2 minor S minor L. Well,
less than.
Yeah. Well, I define the boundary condition, and I shares this value of this value.
Mm-hmm.
The same form, I'm going to analyze the second element and the boundary condition. Well, now I know that the L over 2, the deflection and the derivative will be the same. In this case, I'm going to evaluate the two equations. I'm going to share the constant A1 and A2. The A1 is the first element and A2 is the second element. The same form in this. The space replacing, I'm going to obtain this constant of this problem. Well, I'm going to replace in the first element this constant and the second element is constant. I'm going to obtain the table of points for the shear force and bending moment and deflection. And well, I'm going to graphics the external force and the deflation.
Just a second. I noticed some confusion. No, that's the bending moment. The blue is the bending moment.
Yes, the blue is the bending moment.
Now the bending moment.
And
Okay, go on, go on.
Well, I will take the graphic of the deflation. Yeah, and this
All
is
right, the deflection is
method.
not symmetric, right? It's not symmetric.
No,
it's
it's
not. Okay, good.
yeah. And well, in the fit method, I analyze two elements, element 1, element 2, and defines three joins. Well,
Okay.
I have the diagram. Well, and defines the matrix of the H elements, element 1, element 2, and defines the global matrix, and replace the big values in the join 1 and join 3. Well, I define the matrix, the
External force.
external force.
Mhm.
I collocate the force in the joint 2 and the moment in the joint 3. Obtain the inverse of the matrix and obtain the deflection and the matrix D. And this matrix is the D global. Yeah, and finally, replace the matrix D global and obtain the internal force of the problem. Well, and define this function. And finally, obtain the expression for the moment and the shear force, this expression. Well, I obtain the table points is same of the analytic methods. I obtain the graphic of external force. And finally, obtain the graphic of the deflation. Yeah, I have one observation, but in my Excel, for example, we obtain the first one is evaluate big, for example, yes. I obtain other graphic of the deflation in the finite method.
But there is a problem there because right now, if you have, let me complete. If you have, okay, if you have concentrated forces, concentrated moments at the points where you have the joints, the solution, the analytical solution is cubic. And that coincides with the finite elements. I know this is a very long process and we can make any error here and there and all of that, but this is something that we make a comment in the previous and in this chapter. I insist, if you have bars or beams, in the case of the bars, remember, the interpolation that we employed in the finite element method is a linear interpolation. If you solve the differential equation and you have no distributed load between joints, the solution in that part of the problem is going to be linear. So if you make an assumption of linear and you really have linear, the solution should coincide. In this case, in the case of beams, is similar, but the solution is cubic because the differential equation is fourth order. So if you have external forces concentrated on the joints, you should have exact solution from the finite element method. Anybody who wants to make a comment about the solution of Mr. Barba? Any comment? Any comment from anybody? No? What process did you like the most, Mr. Barba? The analytical or the finite element process? Which one did you prefer?
I like the finite method.
Yeah, finite element method. Yeah, I know. It's
more.
it's easier. Yeah, but the
It's
thing
more
is
easy
this.
to analyze.
The thing is this. The thing is this. Okay. In the finite element method, you got many numbers. A lot. And you will see when you start using ANSYS, you got zillions of values. And the thing is, from there, you have to extract information and make a conclusion. That's what we have to go first with the analytical part. That's what we did in solid mechanics in ship structure. Because in general, finite elements, it's an approximate process. So you have to be aware of that all the time. Okay, thank you very much, Mr. Barba. Anybody wants to make any comment? There is a problem with one of the students because last night I posted the next assignment, okay? And it seems to me that somebody load his work in the wrong place. This assignment is 3A, and the next one is 3B. So if you load your work in the wrong place, please load your work in the correct assignment, in the assignment 3A. Okay? Okay, so let's take a break, and when we return, we're going to make some comments on the implementation of this process into the computer program. Since everybody has been able to complete this assignment, then everybody has a good idea of what's the process to implement. Okay, so let's take a break now.